My name is Cameron Sanders, and this is my project playlist for optimization of polymer solution mixing. Polymers are, a little background, polymers are used in applications ranging from structural materials to biopolymers to everyday plastics. Some widely familiar examples include wool, silk, natural rubber, neoprene, PVC, silicone, and styrofoam. The problem to be optimized is that of predicting polymer solution mixing. So historically, it's been a difficult task, but being able to optimize conditions for mixing can prevent overwork as well as rework. As well, being able to predict optimal conditions for mixing increases the probability of experimental success. For polymer mixing, Gibbs-free energy change must be negative, and knowledge of that principle, higher temperatures will always favor mixing, but temperature can only be increased so much. So we'll use a model that is based on Gibbs free energy principle to characterize interactions. That is Flory-Huggins solution theory, characterized by chi of t. And for mixing solution, the parameters should range between -1 and 2. So chi of t is equal to the volume of a polymer segment times the difference between the two solubility parameters of the polymer squared divided by Boltzmann's gas constant times temperature, all of which are constants except for T. And we know that polymers with a similar solubility parameter tend to favor mixing. And so for the model, there was a multi-part development of a solution. So we developed an initial population, a sample of which you can see on the right, that we will choose from to validate our algorithm. So for each polymer, in the set, we define the solubility parameter, density, and molar volume. And then we applied a constraint that the square root of the difference between two solubility parameters should be between 0 and 1 to consider any two polymers miscible. And then we pick from a set of sample pairs that meet that constraint to optimize with. So we're going to optimize using simulated annealing, which is the method of search and optimization for unconstrained and bound constrained problems based on the actual physical process that is used to minimize system energy. So there's a MATLAB function that we can use that we did utilize for bound constrained simulated annealing. And our objective function here is that of chi. So we had a couple assumptions based on typical lab equipment. We assumed our upper bound to be 483 Kelvin. We set a lower bound that was also based on typical lab equipment, but because of the nature of the objective function, it did not factor into optimization. As well as in the development of our molar volumes for the initial population, we assumed that we had 1 gram of each material, theoretically prepared at room temperature to make 0.1 liters of solution. So we chose 6 pairs that met our solubility criteria for samples and running our optimization algorithm to prove its validity. So we had polyethylene and polyisobutylene that have known to be miscible for over half a century, as well as polyethylene and polypropylene, which are known to generally be incompatible because of high crystallinity that prevents homogeneous. And so we have results here that polyethylene polybutadiene gave us a best function value of 1.44, well within our constraint, while polyethylene and polypropylene gave us a function value of 58, well outside of our constraint, coinciding with known general miscibility. We have PVC and polyvinyl bromide that tend towards the possibility of miscibility. One thing that we didn't previously mention is that the likelihood of miscibility can be increased with increasing pressure of reaction, and this is something that could be introduced to increase the likelihood of miscibility here, even though it falls outside of our -1 to 2 range. And then we have PVC and polychloride, which falls well outside our applicable range, as well as polybutyl acrylate and PMMA fall well outside our range as well. And we have PVP and polyethyl acrylate, which fall well within our range. And then given its low chi, mixing could occur well within our temperature limits opposed. And so of the 6 chosen for the sample, the known admissible pair was shown to be admissible, and the known miscible pair were shown to be miscible. PVP and polyethyl acrylate were shown to be highly miscible for a wide temperature range within our bounds. PVC and polyvinyl bromide shown possibility of miscibility, especially with increase in pressure during reaction imposed. And the other 2 proved to be highly immiscible, even though they met our solubility. Continuing work, we further refine our algorithm by taking into account the aforementioned pressure in predicting miscibility, as well, given that Flory-Huggins only accounts for UCST, incorporating more complex combination of criteria to broaden from UCST to both UCST and LCST is something that could be considered in future development, as well more sample runs could further prove the applicability of the algorithm. Thank you.